Dear Chairman, dear participants, your attention is invited to a report on the topic Diagnostics of Children's Emotional State based on intellectual multimodal analysis of drawings. Employees of the Kharkiv National University of Radio Electronics carry out this work. A child's emotional well-being is closely linked to academic performance, self-esteem, behavior in the class, and the quality of relationships with peers and adults. Projective techniques based on drawings are popular because they help capture experiences that a child is not always ready or does not always know how to express in words. But the interpretation of such works is subjective. Different specialists may reach different conclusions from the same drawing. The goal is to create a model that simultaneously classifies drawings accurately into three emotional categories: happiness, anxiety, depression, and anger and aggression, and produce a clearer report on what the decision is based on. To do this, we combine four feature channels: global context, local objects, color palette, and composition and graphics characteristics, and then weighted their contributions using a lightweight attention fusion mechanism. Objectives. Design an architecture with four branches and a shared fusion model focusing on efficiency and robustness. Capture the global context, the atmosphere of the scene, layered shapes, stroke texture, and overall layout. Detect local objects and convert detections into compact numeric features. Compute informative indicators of color and composition line structure. Conduct experiments and evaluate the contribution of each channel. The architecture of the proposed multimodal diagnostic neural network model present on slide. In this work, we propose a multimodal neural model that combines several types of features from a child's drawing and produces an interpretable result for practicing psychologists. Simply put, the system does not just assign a class label. It shows why a particular decision was made and which elements of the image influenced it. The first branch is responsible for global context. We use EfficientNet B3 as a high-level feature extractor. It reliably captures large shapes, stroke texture, area relations, and the overall composition of the scene. Choosing EfficientNet B3 improves quality compared to simple CNNs and at the same time saves parameters compared, for example, with ResNet 50. Before classification, we prepare each image. We extract the active region, remove white borders and noise, apply constant equalization, and feed a fixed size tensor into EfficientNet B3. This overall view helps where local cues are ambitious. For example, when emotionally meaningful small details are embedded in a calm, well-balanced composition. The global branch adds stability. It compensates for random scanning artifacts and uneven lighting. It also increases clarity. If the report shows that the global channel has a large contribution, the specialist understands that the decision relies on overall composition, shape and line character, and not only on a single object. The second branch is local semantic objects. We train a lightweight YOLO V8 and detector on ESRA annotations covering 55 classes. Typical symbols such as sun, tears, knife, monster, clouds, and others. Small but meaningful markers may occupy a very small part of the image, yet strongly influence the emotional tone. Missing them means losing an important part of the meaning. To keep the representation compact and robust, we do not pass every box into the fusion model separately. Instead, we aggregate detections into 6 numeric features related to 3 emotional clusters. Essentially, we care about 2 aspects for each cluster: how many objects are detected and what share of the image they occupy. This reduces variance and makes the inputs to fusion more stable. The third branch describes the color palette. We compute HSV statistics, a total of 15 features, means and spreads of hue, saturation, and value, shapes of warm, cold, and dark pixels, and distribution across 6 hue ranges. These numbers compactly summarize the palette and depends less on scanning specifics. The fourth branch is composition and graphics features, 9 indicators. Geometry of the main areas, center of mass, a presence of a dominant direction, contour irregularity, stroke density, and ratios of key zones. They reflect whether the drawing is balanced, how smooth or raged the lines are, and how compact the main figure is. All four branches are then projected into a shared 256 dimensional space and combined using attentional fusion. Conceptually, the model learns alpha weights, one per channel, for each drawing. If symbolic content is strong and consistent, the object branch receives more weight. If symbolism is weak, but the palette and lines are expressive, the wages of the color and composition channels increase. A compact two-layer MLP produces the final three-class label. In parallel, a JSON report is formed, class probabilities, channel alpha weights, and several key numeric indicators for each channel. The report is intentionally short. It shows not only what the model decided, but also how it reached that decision. To let the model see both the overall emotional background and small symbols, we use three datasets. Kaggle children drawings, about 500 scans labeled happiness, anxiety, depression, and anger and aggression for training and validating the global branch on real drawings. ESRA, 300 images with object annotations giving us 55 classes to train the detector. An internal pilot, about 200 scans for external checks of interpretability and robustness across different styles and techniques. The pipeline is unified. We extract the active region, normalize contrast, and prepare two versions of each image, one for the global classifier and one for the object detector. This helps preserve proportions, make small symbols recognizable, and at the same time give the global branch its best input. We account for class imbalance at the sampling and loss levels, and we use augmentations, flips, mixed up, partial masking to reduce overfitting. On the combined test, the multimodal system shows about 85 accuracy and clearly outperforms single branch baselines. Each branch sees a different part of the story. The global CNN captures atmosphere and stroke texture, but can be confused by very vivid and high contrast scenes. The object branch captures strong symbols, for example knife or tears, but does not see composition and color. Color and composition add tonality and structure. Their combination via attention fusion yields gain in both accuracy and clarity. We analyze channel contributions. For clean happiness cases, color and composition more often dominate. For some anxiety depression cases, the global context becomes decisive. The scene is muted and low contrast. For anger aggression, local objects can tip the scale even with small area if their signal is consistent with the palette and line structure. This picture agrees well with practical observation by specialists. Emotion in a real drawing is set by several cues at once. How does attention behave in real example? If the palette is loud, but the storyline is clearly positive, the attention mechanism often does not give color the decisive role. More weight goes to object and composition, and the prediction remains happiness. In other case, indicators of aggression are detected, but they are very small in area. Then the contribution of the object channel may be moderate, and the outcome is determined by a combination of global context and line structure. This adaptability helps resolve conflicts between channels and reduces false positives when one signal pulls in one direction but two others balance the conclusion. And conclusions. We presented a multimodal hybrid model for diagnosing emotions from child's drawings. It combines four feature channels, uses attention fusion to adaptively weight their contribution, and produce a transparent JSON report. In practice, this provides scalable screening and increases trust in the results because it's clear what the decision is based on and which factors influence the conclusion. Limitation remains. Collages and heavy watercolor washes are challenging. The model does not yet use explicit age and culture metadata, although symbolism may differ. In the future, we plan to expand datasets by region, age, and drawing techniques, add such metadata to the pipeline, further tune probability, calibration, and uncertainty thresholds, study attention behavior in borderline classes in more detail, and confirm the results on independent samples. Thank you for your attention.